So I'm Christian Raidel from the Technical University of Chemnitz, and I'm here to introduce you to my work in form of a poster. I was interested in the Azabad doping of graphene. So in this case, it's monolayer graphene, which we see here on these two sides. The idea is that there exists a doping model, and we're trying to probe it with other molecules. So in a previous work, you can see that there was a doping efficiency calculated for C60F48 and for F40CNQ. And the idea behind was to probe the efficiency of taking one charge carrier, in this case an electron, from the graphene sheet towards the molecule. And you can see in this work that it is still unity, for example, for a coverage of 0.15 monolayers of C60F48, while it dropped to 0 for F40CNQ. This is also calculated for another temperature, and our aim was to probe this with two different molecules. So at the first side I can show you the work on manganese phthalocyanines. So basically what we took was a monolayer sample. You see the typical signature of a bulk, graphene and the buffer layer components. Obviously we had some oxygen on the sample, and then we evaporated some manganese phthalocyanines. You see the typical features like the benzene, the pyrrole and the satellite peaks over there. It's all convoluted in the spectra, and in this part we're only interested in the graphene position. This gives us the doping, and we calculate a total doping of 0.11 electron volts, so that means it's p-doped. This can also be seen with angular resolved photoelectron spectroscopy over here. So you get the evolution of a clean sample surface, the monolayer surface, 1.5 and 5 monolayers, and you see a slight upshift of this Dirac cone, of this cone-like structure, towards charge neutrality. This is in a nice agreement with the information we got from XPS, so it's p-doped by 0.11 electron volts. Yes, you can also see from NextEffs, this is mainly done by, calculated by a colleague of us, that this molecule stands up. The preliminary result will be that it's standing 30 degrees up from the sample surface. Yes. Let's come to the other molecule we investigated. This was done on bilayer graphene, so it is C60F48. Remember, we had here the monolayer case. This shall be the bilayer case. The idea or hope was, does it shift to charge neutrality? What happens? Does it maybe open a band gap? And what we observed was the evolution of some spectra from the clear sample towards 1.2 monolayers, and we only saw some variation in the band banding. So basically what we saw was that there was nearly no peak at the carbon positions where we expected the molecule to be, and also a few amount of the graphene shift. From other work we would have expected some more signal and some more shifting, so we evaporated a huge amount, that's 1.2 monolayers, and looked at the time evolution, and we could indeed see, this is on these positions here, that there is a signature at higher bonding energies. This is the fluorine induced, this is the fluorine region over there, and what you can see is that it goes down the longer we illuminate it. Let's go to this side maybe. This here is the convolution. It's very, very many peaks in there. So basically what you have is from graphene the buffer layer, which is here. You can see this at this photon energy. We know it. We estimated it from a higher photon energy. We got the graphene component, which is the Psi blue, and the buffer layer components. Okay, same work, same procedure as the other work, but inside these peaks, inside the spectra, are also the parts from the fluorinated molecule. So this are the green parts, and from the carbon from this C60F48, this is the red parts here. And we could estimate